thank you for organizing this opportunity. So this is the work done with two graduate students in IIT Kanpur. And this is, I'll tell you about some results, mostly numerical, some saddle point results as well on highly excited S matrices in bosonic string theory at tree level. And these aspects are interesting because motivation of this work is to understand how thermal signatures arise from S matrix elements. And what I, oops. Yeah, and what I want to focus on is, and what the main message that I want to give is that if you have some chaotic amplitudes, if you have some chaotic matrix elements, then if you do a coarse graining over them, then they reproduce some thermal signatures, and string S matrix for very highly excited, involving very highly excited strings will have this property. And this goes in the realm of things to do with eigenstate thermalization. So where the question is to ask, when does a closed quantum system thermalize? And this question can be phrased purely in terms of matrix elements. Okay, and we'll see that in string theory, provided one can compute them at tree level and give some, let's try to understand how this happens. Please feel free to ask questions. There will be many parts which will be heuristic, and I will hope to have more clarity for myself. So let me first describe chaotic scattering. So the chaotic scattering is best understood classically. So if you have some scatterers, so think of them as hard disks with perfectly reflecting boundary conditions, then you send in a probe, then it will keep reflecting and then it will go out. Right, and then it will depend, of course, on the potential and then also on the initial angle. And let's say you measure how much time it takes for this particle to come out of some region. Okay. And then you will see that, that for some angles, there may be many scatterings. This time can be very large. And it will depend sensitively on the initial angle. So depending on the setup of the potential, it can be very sensitive on the change of angle. That gives a notion of chaos. So for example, these are some simulations done. So for different angles, you see that there are some angles where this time to escape a rectangle diverges. And then near this, the function behaves erratically. So this is the time to escape as a function of this angle. This is that scattered plot. And in fact, this is known in literature. And if you have, for example, this, so there can be many going back and forth here. That gives a large time. And means a way where chaos manifests in this plot is if you zoom in, then you see self-repeating patterns. The fractals also. Yeah.
Does the time really diverges or just very large?
Very large. Very large. Eventually it will go out. There will be very, like, measure zero trajectories which will keep doing this for that. You will not resolve that, essentially. But the chaos is in, so to discuss chaos, you have to create an ensemble. So the ensemble can be created by shifting the potential slightly. So I shift this potential slightly, then this observable as a function of this initial angle, this kinematic variable, this can change a lot. So the question of chaos is how things are dependent on the change of ensembles. So I change my initial condition slightly, change this initial disk's position slightly, and this, if this function exhibits totally different erratic features, if it's a chaotic function to begin with, then one can define Lyapunov exponents and so forth. This is what people have done in chaotic scattering, and this is from those plots, but resolution is not that great, but you can still see there are some self-repeating patterns. So I zoomed into this regime, I see some self-repetition. Again, I zoom in here, I see some self-repeating. And naively, these two plots look the same. This is for the other shifted trajectory, but if I zoom in, then I'll see they are actually different. Okay, so in the sensitivity to configuration change, if it's chaotic, this thing will show. And the analog in quantum scattering is the observable is the S matrix, and this was the place where Wigner introduced random matrices to explain experiments done with neutron scattering through heavy nuclei, uranium, thorium, and you see these are the peaks. And these peaks, if you make a list of these peaks, make a list of the spacing between the peaks, then that level spacing, it follows something called a Wigner-Dyson distribution, which can be explained using random matrices. And in this case, the random matrix is the Hamiltonian of the heavy nucleus. So the energies, the eigenvalues are the eigenvalues of the random matrix. There is a nice review where these historic plots are put. But to do some random matrix type analysis, one needs many resonances so that one has an ensemble to do statistics. And that is where actually we'll see string theory will help us. So another place where string theory will make contact with this story of thermalization is black holes. And black holes are also tied to chaos. A lot of recent developments, also developments from some time back. Classical trajectories are known to be chaotic. Then there is this story about scrambling and how these are related to some classical chaotic properties. I'll just briefly just going over this thing because some things I will say, some features of the S matrix will mimic some features of black holes. And then there is this motivation from Polchinski's 2015 paper where you have this series of resonances. If there is a black hole involved in the S matrix, and then from the resonances you can derive a time scale. And if you have many resonances, maybe you can reproduce the big time delay that you see in black holes. And of course, they are thermal objects. So the question is, if we have an S matrix involving black hole states, can we understand any of the emergent thermodynamic properties? Okay. So that's the main kind of question, or where we want to aim for. We'll not be able to reach, of course, but we'll try to. This will be the motivation at the back of the mind. Any questions? Yes.
When you say an S matrix involving black hole states, is black hole one of the scatterers, or is it like on a black hole background that you're doing?
Yeah. So I'll be very explicit about this state. So give me just 2 slides. I'll come back. So I'll talk of a setup which is the Horowitz-Polchinski-Susskind correspondence, where there is a particular where highly excited string states are supposed to capture some features of black holes. So those will be the scatterers for me. And I'll scatter a tachyon. And the notion of thermodynamics, quantum thermodynamics in closed quantum systems are best explained using ETH. And this is what I mean by quantum thermodynamics. So if I have, let's say I have a spin chain. So with some, so there's a 1D spin chain with some non-integrable couplings. And I start with a non-equilibrium state, which is not, let's say it's highly excited state in the middle of the spectrum, and I look at some local observability. So spin at site 3, let's see. And I plot it as a function of time. Then if it thermalizes, then this will be, of course, a time-dependent value, but if this system shows some thermalization with respect to this observable, then all these fluctuations will settle down about some mean. So that's quantified by the ETH, which talks about the mean and the variance about the mean. So for the variance, if you just work out the variance, you will see the variance is proportional to, is given by this sum over the off-diagonal matrix elements of the operator in the energy eigenbasis. So you want this variance to be very small for thermalization. Only then the fluctuations will stay near the mean. So this is what a demand of ETH is. And other demand of requirement that you want from thermalization, of course, is the expectation value of the observable should match with some thermal expectation value. So the temperature is to be solved from this equation. So you have a pure quantity here, pure matrix element here, and you have a thermal observable here. You solve this equation for the energy, and you solve for the temperature from this equation. So for every given excited state, you can associate a temperature, and you will say that if your system thermalizes, it will thermalize to that particular ensemble. And the criteria that this is a working definition is that these variances are suppressed. They are entropically suppressed because you see there are e to the power entropy number of such terms. So they have to be at least entropically suppressed. And this goes back to von Neumann's thesis, essentially. And random matrices have arisen also in the discussion of ETH. And in many body systems, what people have observed in spin chains is that you look at matrix elements in many body systems in spin chains, and only after you do a coarse graining, it turns out to satisfy ETH. So you still have to do some kind of averaging over very thin dado energy windows. And we'll see that we will also have to do some kind of a coarse graining when we talk about S matrix elements. And the intuition is that if these matrix elements are chaotic, if they're random, then if I do the coarse graining, then there is a lot of cancellation, and that can give you this suppression, the entropic suppression. So that is what will happen.
But wasn't the original, ETA supposed to be without any coarse graining?
Yeah, it was without any coarse graining. So
the
typical state should have that property, but so one limitation is we can't access very large level states numerically, so we can't really look at typical states. So we will always rely on some notion of coarse graining. But the original statement is to evaluate matrix element by matrix element. Yeah. So we will need a theory which will have S matrix with many peaks and contains black holes. So even at weak coupling, we'll see that there are some setups just in bosonic string, which is this setup. So this is the correspondence point argument of Susskind, then developed bit by Horowitz and Polchinski, which is basically the statement that if I consider a very small black hole whose length is, whose Schwarzschild radius is the string length, then if I adjust the masses so that the mass of the black hole matches the string mass at some level n, then the phases should be indistinguishable. They will have the same entropy. So the number of states here for the black hole is of course proportional to the area of the black hole, and for the string at level n, the number of states grows exponentially with square root of n. So the entropy grows like square root of n, and if you are at the correspondence point, then these two scales agree. So that's the statement of the correspondence point. So what happens is basically a little more in detail. Same thing. So radius of the black hole is G Newton, which is G square alpha prime times mass of the black hole, and the radius I demand to be the string length. So that tells me what my J string needs to be. And good thing here, if you solve this, you will find J string goes down with increasing level. So maybe at very high levels, you can limit yourselves to tree level string theory, and still you can see some features. So that is the regime where we will do our calculations. We will do calculations at very large n, and we will do tree level calculations. So we need a string state at large level n. The tricky thing is that it needs to be a physical state. The entropy is reproduced because A over G Newton goes like R square over G Newton is G square alpha prime. R square goes like alpha prime. G goes like 1 over n power square root. So this goes like n power minus f alpha prime cancels, goes like square root n, which is how the string degeneracy goes. So that's the rough argument why these states can have some black hole-like properties. And here again, already one has to count all the states at that particular level to reproduce the entropy. So there is a notion of coarse grain. Okay, and no need to talk about detail about this slide. So a generic excited state will be made out. So I'll be in bosonic open strings. And this is a generic excited state. Tricky thing is to impose this constant. Level by level, it gets complicated. This is the Marshall condition, m square, the space-time mass of the excitation goes like square root of n over square root of alpha prime at large n. And physical states, you have to impose the Virasoro constant, and that, for example, at level 1, it picks the photon. And at level 2, it, for example, will pick the correct polarizations, the physical polarizations. And level n, it becomes complicated, but fortunately, there is a clever way of doing this, which was the work of DDF. Where what one does is one starts with a tachyon, on-shell tachyon, and starts hitting it with photon vertex operators. And then if you hit it with photon vertex operator, everything will appear in the OPE. And then in the OPE, you do a projection onto physical states by just do a contour integral. And this is how you can actually get a font for these DDF creation operators. So these are called DDF creation operators. They come with a polarization and they're indexed by the wave number of the photon with which you have made this operator. Okay, and then this is how it looks like. There's a Schur polynomial, and it's basically made out of, it's a polynomial of derivatives of the worldsheet field. And but one can prove that this will satisfy the Virasoro constraints. Okay, and then they have the physical polarization. They are indexed by a polarization. So for simplicity, I will take all the photons to have same polarization.
Is there a reason why you're using a bosonic string instead of superstring?
No, for simplicity, and also because recently these kind of amplitudes were computed in bosonic string. So I wanted to compare with their result. So, but one can also do these constructions.
I guess I'm worried about the tachyon.
Yeah.
The-
So we will have to live with the tachyon in this case.
But are you taking it as like a case study for the superstring, or?
Yeah, one can think of it like that. Yes.
Presumably tree level is not a concern, right?
Yeah, we'll be all at tree level. Yeah. I'll have some comments at the later. Okay, and level n, these are can be written in terms of full polynomials, and A generic state can be represented as a partition of an integer, where the partition is the integers are the frequencies of the photons with which you make it, and the degeneracy is the number of such photons. So for example, this is a 7 by square root alpha prime mass state representation. This is a nice paper where they do nice cataloging of this technique. Okay, and then Gross and Rosenhaus computed the amplitude, tree-level amplitude, with one of these highly excited strings and two tachyons. This is the answer. So the answer depends on one kinematic parameter alpha, which is, sorry, I'll call it chi later, but what it is essentially this. So you have h going to tt. So this is, so we will concern ourselves with h, but the diagram is the same. So the angle which this amplitude is a function of is the angle between the polarization of this highly excited string state and the direction of the decaying tachyon or the ingoing tachyon. So that angle, so the thing depends on that angle. The answer depends on that angle. So this is that angle, 0 to pi. There's a symmetry from pi to 2 pi. And if you plot this as a function of this alpha, you see that it sensitively depends on the microstate. So if I change my microstate slightly, so both are answers for level n equal to 50, but for different partitions. So if I change my partitioning slightly, this answer changes a lot. And the idea was in this paper that maybe this can give a notion of a chaotic amplitude. So I'm changing the microstate slightly and my amplitude is changing a lot. Okay, and then mathematically it's easy to understand why this is happening, because these are just trigonometric functions, multiply many of them together, raised to powers. So of course it will depend very sensitively on the powers. But maybe approximately there may be a random matrix description. That is what we are after. And what we will consider is more than one excited string amplitudes. So we'll have more than one. Because we want to also look at how things depend on the polarization of the state. Okay, this randomness, the chaotic feature, how does it depend on the polarization of the state, and can we understand what class of random matrices appear in these observables? And then finally, we want to understand how some kind of a thermal behavior emerges. And for that, if we want to consider, say, a 1-point function in a thermal background, then we should have two heavy states. Because if the heavy state is like a black hole, then there should be two of them. So therefore, we consider more than one highly excited, and we will see some relations with some scales of the black holes at this correspondence point will just follow from these answers after I do a course. Okay, so the answer takes this form. So here, so what I have is so these blues are the highly excited states. So there's a highly excited state sitting at rest, and then it decays into another highly excited state and attached. And this is made out of a photon with a polarization. Also, so this is made out of the same polarized photon. So there's this angle. So things will depend on this angle. And we'll see how things depend on this angle, how it changes if I change the if I change these states, if I change these microstates.
So are these excited states of the same level, or
they can be different levels? So kinematically, you will get a non-zero amplitude if vacuums, or if there is a photon. But as soon as this is a higher level, that's not kinematic. It will not be kinematically allowed. Okay, but these can be for a tachyon. These can be some N1 and N2. You can satisfy constant. So I'll not go over the calculation. Let me show results. So here, so this is amplitude between two heavy states with N1 and N2, and this is another amplitude with the same N1. So this is just different partitioning of the same N1, and this is different partitioning of the same N2. And the amplitudes look very different. See, the number of resonances also have changed a lot. And actually, one can show that there is a way to understand this approximately from a random matrix, which gets better when n is large. So these are computed numerically, but these are exact. Numerically, as in just these multiplications are done numerically. But this is an exact thing. Okay. And now, if you make a list of those peaks, so to make contact with random matrices, what I will do is what was done for the heavy nuclei scattering. I will make a list of these peaks, these resonances, and make a list of the level spacings and try to see if it follows a random matrix statistics. And then it turns out that you get these HHT amplitudes with increasing n fit well to the GOE random matrix ensemble. If I take N1 and N2 same, then this happens. If I take N1 and N2 different, then it's not clear what happens. This is a paper by these gentlemen where they considered the gross Rosenhaus amplitude, and this is a quite recent paper, and there they make the statement that it goes to a GUE. So what might be going on, what we think is because if we have exactly the same state on both sides, then probably it's time reversal invariant. The process is time reversal invariant. Then, and if it's time reversal invariant, then it falls in the GOE class. So, but this is not clear why it is GOE, but it seems numerically one approaches GOE. One can do other kinds of tests. One can do something called the Kolmogorov-Smirnov test, where one looks at the entire probability distribution and looks at so this is the probability distribution. This is coming from the data, and this is the probability distribution with which you are comparing. And you look at the distance between the cumulatives of the two, and you take a supremum. So if this goes to 0, then the probability distributions are close to each other, and this distance goes down with increasing n. And the effect of polarization is also clear. So if I take the HES states to be orthogonally polarized, then it takes a larger n to achieve the random matrix-like effective behavior. It achieves a faster random matrix effective behavior when they are not orthogonally polarized. That's probably, again, these are just heuristics. This is probably because there are more choices I can make. So the phase space is larger, where zeta1 is not orthogonal to zeta. So this is a more restrictive choice in some measure. So this is again heuristic. Okay, and then I was talking about coarse graining and extracting some black hole-like scales. And so one thing we can ask, what kind, if this really corresponds to like a 1-point function in the black hole background. So if this is a black hole, then this is a black hole emitting some quanta and then going into another black hole. Or I can think of the reverse process where it's absorbing some quanta and going to a black hole. And then what the temperature of this black hole should be, and the expectation is it will be the temperature of the black hole at the correspondence point. And the temperature of the black hole at the correspondence point is proportional to G times M, G newtons times M. And if I work out, then there are no factors of n with certain. Because M goes like square root of n, G is G squared alpha prime. G squared goes like 1 over square root of E. So the factors of n cancel. So there should not be any n scale in the temperature. And if it's a 1-point function, then it will be dictated by the temperature. So one will expect there will be no n scale if I do the coarse graining of this amplitude. And it is at this level that one has an answer. Because so what one can do is one can take exactly the identical partitions on both sides of that expression of the amplitude, and one can sum over all the amplitudes which keep n fixed. Okay, notice I am doing a coarse graining over amplitude, not over mod, not over the not what we do in field theory where we mod square it and then add it up. So I'm coarse graining over amplitudes. And if this is just Lagrangian multiplier which enforces the constraint that the level is capital N, and then this integral can be done. What happens is the amplitude exponentiates and gives this expression, and chi is again that angle, so it depends on that angle between the polarization and the photon, the tachyon escaping. And this function, if I plot this function as a function of chi, it behaves in this way. There is a maxima exactly at pi by 2, whose value is exactly pi by root 6. So, if you average over all the angles, if you look at this function over all chi, then it's so exactly at pi by 2. This is 0, so it's an order 1 number, and then there are e to the power minus square root n corrections to it. So the leading order doesn't have any n scale. So this is the way in which we see the correspondence point temperature. Okay, but there is also another argument which is also quite heuristic. This is using the holographic, the gauge gravity duality. One observation made in gauge gravity duality, which was that if I have ADS Schwarzschild black hole or ADS Reichenau-Nostrom black hole, which was worked out in this paper, and the original observation was in this paper, then the 1-point function, of course, one can get it by solving the Klein-Gordon equation or by looking at geodesics. But if one does this very particular analytic continuation, that one complexifies delta and takes the real part to infinity, then there's one geodesic which dominates, which goes inside the black. So this was the observation in this paper, and the motivation was that under this complex analytic continuation, one has information about some scale inside the black, or scales inside the black. And this continuation I can think of like taking the flat space leap. I can think of. So I'll probably expect that so what appears here is the time to singularity from the horizon to the singularity. So this time to singularity should also not show any n scale at the correspondence point. So this is another very heuristic argument, and time to singularity indeed again depends only on this quantity. So this, I'm not saying anything new. It's the same observation as the temperature. But what is more interesting probably is the connection with ETH, and there we'll see that this coarse graining seems to play a role. So ETH is, as I was telling you, is a statement about off-diagonal matrix elements, the fact that they are exponentially suppressed. And while we cannot analytically establish this for different n1 and 2, but if we take n1 and 2 same, but we look at the off-diagonal elements, so we are looking at partitions which are different, but they are the partitions of the same integer. Then one can show that these are exponentially suppressed. And numerically, we can do this for different N1 and N2. So what we do is we set I not equal to j, and we sum over these amplitudes with I not equal to j, divide by the norms of these 8 states, and we are doing an average. So we sum over the mode of this because we don't want to, because we can't resolve this RAB factor. And then we divide by the total number of terms we sum. And then from here, we can actually extract this. We can see that there is this exponential fall-off, and we can extract this ETH function f of omega, which has a right behavior, because that f of omega should also decay exponentially with omega. So we get this numerically, and again the matches are better when the angle is close to pi by 2. When angle is away from pi by 2, then there are oscillations in this extracted f of omega. So this the fact that this pi by 2 is dominating scattering and thermodynamics is tied to the fact that actually it's a rotating black. This understanding we don't have properly, but there are some semi-classical scatterings which have been worked out in literature. For example, if you consider Klein-Gordon equation scalar fields in a Kerr spacetime, then one can show that actually the scattering cross-section diverges when this angle is pi by 2. So it's the same kind of thing that one is observing here. That at pi by 2, so this pink line is the line of this polarization axis, which is the axis of rotation of the black hole, and this is the angle. This pi angle is the same pi angle. This is again bit rough. Okay, and then there are these amplitudes that we also computed, which with one. So we computed one with 2 heavies and 2 tachyons. So the amplitude with 1 heavy and 3 tachyons were computed by these people. And there, what they observed was the amplitude takes the form of the Veneziano amplitude. So this is in terms of S and the scattering angle theta times the dressing factor. And this dressing factor has the same form as the 3-point function of heavy tachyon tachyon. So this is how it looked like, and if we do the computation with 2 heavies and 2 tachyons, then what we observe is also we observe this structure where we have a part which is like the Veneziano, but it shares momentum with this dressing factor. It's like a convolution, and this dressing factor is exactly the one we had with HHT. So what happens is that the chaos gets inherited from this factor H. So if one looks at the residues, then one will again find random metric statistics in the residues. For example, the leading residue, if is at S equals to 2n, so with alpha prime equal to half. So the residues again has peaks, and if one does the statistics of that, one sees level repulsion. And one can also take the largest fixed angle limit, so like the Regge limit, and one can check it satisfies the Regge boundedness. And so the characteristics of these amplitudes are that they grow as s to the power j by 2. So j for these heavy states is the sum of the length of partitions. So that's j. So it grows like s to the power j by 2 times these factors. And because we have 2 heavy states, we have 2 of these factors, s to the power j1 by 2 and s to the power j3 by 2. So these are again some characteristics of these amplitude. One can also have a notion of a typicality. So one can ask which partitions dominate at large S, because at large S probably one expects things to be more thermal, and one can show that. So for fixed angle scatterings, as I increase S, then the small partitions start dominating. So we will expect that we follow the typical partition curve. There's another thing also which one can calculate, which is because one has now the 4-point function 2 to 2 scattering, so one can look at form factors which have information about the structure. So and to extract the form factor, what one does is one looks at only the T channel amplitude for low momentum transfer and extracts out the leading pole. So there is a photon pole, and then so it will be multiplied with a tachyon form factor and a heavy form factor. Tachyon form factor one introduces this was computed from the Veneziano in '93, and for HES you can compute it. You will get this answer, and from the form factor you can extract. So you can do an averaging, and then you can extract effective length, effective size of these strings, and so basically you do a inverse Fourier transform with respect to Q that gives you a distribution, and then if you have the distribution, you can check what is the spread, and that spread goes like square root of n. The square of the spread goes like square root of n, and this falls in the realm of these results where these long strings are supposed to have random walks. So if I look at a wall line trajectory snapshot, then it will look like a random walk. So that is what. So this is nothing new, but this is computed with these HES states. Okay. So let me summarize. So states at large n, the Horowitz-Polchinski Susskind support of this was that if you if you count all the states, then you get area worth of microstates. But you now there are many results from various people, and also what I showed you, which also support that there are other quantities which also support this correspondence. So firstly, you have if you look at HHT S matrix, and if you look at the peaks, the statistics of the peaks has some random matrix features. Also HTT also I should have added. And if you do a coarse graining, then the amplitude exponentiates. If you look at the diagonal piece, then it matches. It has the right scales as expected for the black hole at the correspondence point. Off diagonal under coarse graining, there is entropic suppression. It will be nice if one can show. If I choose a state which will be typical at large n, then it also has the suppression. I expect one probably will be able to show on Pute's numerics, and then in the range limit largest fixed angle, one sees that typical states probably dominate. So this is not this is just a visual expectation. This is not we have not fitted the probability distribution, and then form factor one gets random, and many things to do. So there was a question about superstrings, and so there is this massive degeneracy. So it's expected to break if I include loop corrections. So it can happen that even the mass spectrum may show some random matrix behavior. So that's a work in progress, and it will be exciting to do this. So these DDF states also exist for the ADS3 string. Gopakumar, Jabadial, Eberhard. So it will be interesting to check for these features in those states. Maybe it will mean something holographically. And field theory limit can be taken. So the answers are non-perturbative in alpha prime. They are perturbative in G string. So maybe these are interesting effective field theories which have this property of chaos. And then because we have a excited string S matrix, we can deform and try asking about bootstrap, S matrix bootstrap. Thanks.
I mean, one thing that was important, that correspondence point was the, you need some sort of self-gravity, right?
Oh, yeah.
The string is much bigger than the black hole, but,
Yeah.
but that's.
Yeah, the string is really big. So string goes, size of the string grows with the mass, but the entire thing out is to fix the G string, we had to conjecture that it will be of the size of the black hole of the string length. So that's happening because we are ignoring the self-gravity. Because that's non-perturbative question.
Yes, you want to sort of decouple that from the random matrix. I think that's not important.
Not important for this, but it'll be nice to try to maybe if I add in these string collections to see whether it goes towards that, the size keeps shrinking. So that's another motivation of doing the G string. And there was also a paper by Tristan McLaughlin and company where they showed for n equals to 4, the 1 over n anomalous dimensions have a Wigner-Dyson distribution because it's a non-integrated, it's a chaotic spin. So it will be in the same expectation.
There, let's say, the ideas matrix in terms of some amount of time ordered correlated to get the usual sense of the chaos in terms of some level of experiment. Or is that not possible for some string scattering?
Interesting. So you mean of the target space-time fields? You want a OTOC for the target space-time fields? So yeah, I don't know how means because here you at least perturbative string theory you only get on-shell amplitudes. Yeah, I don't know from on-shell amplitudes if there is a way in field theory to get OTOC you can do the same operation, but doesn't seem likely from on-shell amplitudes you can get maybe the correlators have information, the singularities of the correlator has information about, I guess, the on-shell amplitudes, but you need something more, probably, not sure. Yes.
Consider heat relativity, then is there anything corresponding to these random matrix type states on the heat side?
Yeah. So these, yeah, I would guess these will be very complicated. Trying to think in terms of Wilson loop, like operators or.
The reason I'm asking is that
Yes.
just plain old pedestrian QCD.
Yes.
Then there is such a thing that there are random matrix type
Yeah,
states.
those are bound states. Yeah.
And it just came to my mind.
Yeah.
It reminds me of
I see.
that, but I don't know whether it has anything to do with what you are
I have not thought about this at all. But these are definitely these are features. These are going to be some features of bound states because you have well-lived resonances.
But these are not bound states, these are actually fork states.
Yeah,
So these are,
but these are quasi-stable. I mean, bound in the sense of they have a narrow, almost narrow resonance. Yeah.